Hello, good morning, students. Now we come to friction, the equilibrium of a heavy body and an inclined plane under any force P. So, how to find the forces acting on a rigid body which is acting on an inclined plane. Suppose here this is an inclined plane of inclination alpha to the horizon, and P is a force which act, and this is a heavy body which is acting on an inclined plane, and P is any force of inclination theta to the horizon or to the horizon of the plane. So here P is the force of inclination theta with this inclined plane, and R is the normal reaction, means force perpendicular or the normal perpendicular to this body, and W here is the weight. This is a rigid body you have here. W is the weight which acts vertically. This is W which acts vertically downwards, and alpha is the inclination of this inclined plane. So there are two cases here. Two cases will arise here. One is when the body is on the point of sliding down, and the other is when this heavy body is on the point of moving up. So first case is when the body is on the point of slipping down. So in this case, as you can see in this figure, so see, suppose this is an inclined plane, and W is the weight, this is a body, and R here is the normal reaction you can see from this figure. So here this forces, there is another forces because W is acting vertically downwards. So you resolve these forces W along the plane and perpendicular to the plane. So along the plane, the result part of this force W will be W sine alpha, and perpendicular to this plane which is acting in this direction will be W cos alpha. Similarly, the result part of this, if you have force P of inclination theta to the inclined plane, then the result part of this force P along the plane will be P cos theta, and perpendicular to the plane means this one, which is P sine theta. So therefore, when the body is on the point of sliding down, the force of friction always acts in the opposite direction. If the body is moving downwards, the force of friction mu r acting upwards. So mu r will be in this direction. So how many forces are along this plane? They are mu r p cos theta in the same direction, and W sine alpha in the opposite direction, acting in this direction. And what are the forces perpendicular to the plane? They are the normal reaction, the result part of this force perpendicular to the plane, that is P sine theta, acting in the same direction, and another force W cos alpha, that is the result part of this weight W which acts vertically opposite to this forces. So these are the forces along perpendicular to the plane, and along the plane these are the forces. So by resolving these forces along and perpendicular to the plane, as you can see in the figure, so along the plane they are this one. This is W cos alpha, that is the result part of this weight W. This is W sine, this is W sine alpha, and this is W cos alpha. So this is alpha, inclined plane. R is the normal reaction, and P sine theta is the result part of this force P of inclination theta, and here it is P cos theta. And since the body is on the point of moving downwards, so the force of friction mu r is also acting. So by resolving the forces along and perpendicular to the plane, so along the plane we have this one, mu r plus P cos theta will be equal to W sine alpha. Name this as equation 1. And perpendicular to the plane, these are the forces, that is R plus P sine theta, is equal to perpendicular to the plane. This is another force. This is W cos alpha. So eliminating R from here, so it implies that R here is equal to W cos alpha minus P sine theta, equation 2. So eliminate R, substitute the value of R in 1. So therefore 1 reduces to P cos theta, and then plus mu R, here you replace this R. Mu is the coefficient of friction by W cos alpha minus P sine theta is equal to W sine alpha. Or you can write here by rearranging this, you have P cos theta plus mu W cos alpha minus mu p sine theta is equal to w sine alpha. So bring this mu w to this side and this to this side we have, or you can write p into cos theta minus mu into sine theta. By bringing this to this side you can take w common, you have sine alpha minus this one mu cos alpha, which implies that p is equal to w into sine alpha minus mu cos alpha divided by this one cos theta minus mu sine theta. But we know mu here is equal to tan lambda, the coefficient of friction. So tan lambda, now you replace mu by tan lambda. So we have here w into sine alpha minus tan lambda into cos alpha divided by cos theta minus tan lambda into sine theta, where lambda is the angle of friction. So this implies that P here is equal to W. This tan lambda there, you replace it by sine lambda upon cos lambda and dividing, so you have cos lambda into sine alpha minus sine lambda into cos alpha divided by cos lambda into cos theta minus sine lambda into sine theta. Why? By replacing tan lambda equal to sine lambda by cos lambda. So when you sine lambda by cos lambda, when you take the LCM here, that cos lambda from the numerator and the denominator will get cancelled. So what remains here is this, and according to the formula, this is nothing but w into sine of alpha minus lambda with alpha greater than lambda. When the body is at the point of slipping down, so alpha is always greater than lambda. So we have here sine of alpha minus lambda divided by cos of theta plus lambda. So this implies that P, and P here is minimum. The value of P is minimum when the denominator is when cos of theta plus lambda is maximum. And the maximum value of cos is equal to 1. So therefore P minimum will be equal to W sine alpha minus lambda. So similarly, when the body case 2, when the body is on the point of, so I'll stop here, and in the next video I'll discuss with you with the case of when the body is in the point of moving up.